Hello friends, how are you? I hope you are absolutely fine. I am Pratham. I am here on my YouTube channel Learn with Pratham, and today I will discuss about Adaboost algorithm. How this Adaboost algorithm is fitted, how this Adaboost model fitted on a particular training dataset. Let us suppose just we have a classification problem in this ways. Okay, so up to this is my dataset. Okay, up to this way. These are the computations. So, I'll come to this particular part from wait this particular part later. Let us suppose this. Okay, these are the row numbers, and this is one the feature one and feature two. Corresponding there is a y, there is a outcome. So we have to train this data set and we have to create an Adaboost model. So just already about in this name, from the name itself, that Adaboost algorithm is basically a boosting technique. So what is the intuition of the boosting techniques? That is nothing but, suppose if we for the boostings, what we do basically, we try to investigate the weak learners, and the combination of the weak learners will make a strong learner. Okay, so this is the main intuition of the boosting. So I think this particular thing is pretty clear to you. So let's quickly jump for the Adaboost algorithm. Okay, fine. What we have to do, just we have to create for this particular data set up to this. So these are the outcomes, plus 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 plus. Just for your case, when you train, these positives are 1 and negatives are, let's say, zeros. Okay, so we have to predict it. So initialize the weight wi equals to 1 by n. So what you have to get, you will get it. Let us suppose we have, in the training data set, we have 10 such entries, and what will be the weight? Weight will be 1 divided by n equals to 1 by 10. That is weight for each and every cases. That is 0.1, 0.1, 0.1 like this. Okay, this is pretty clear. And start with the null classifier, that is 0. Okay, so fine. For in the zeroth step, you are predicting, just you do have a null classifier, nothing else. That is for the initialization. That's not the part of the algorithm even. So now from here, this step 2, our main computation begins. Okay, so what do you have to do? That is generate the training dataset by sampling wi. So what is if the weight is this, then how can we make these samples? Because we'll not grow the will not train in the first step all the entries. So what we'll do, how this sampling works, because all these are the same weights, so you can basically, what you can do, you can take the random samples. Say let us suppose just you want to grow the tree, you want to make the classifier from, let us suppose you will train only 7 data, so you can randomly take the out of this data set, you can randomly take 7 data set data points. Okay, so because these weights are same, let us suppose if your weights are not same, so if your weights are biased, then what you have to do, you have to generate and random, you have to generate a random number between this range, and you have to, so go on and go on. So here you can, the first step, all the weights are same, you can choose random samples. You can choose the random samples, and you can grow the tree. Now here, just we will not grow the trees in the same fashion what we had done for the random forest or decision tree like this. So basically, that's basically for the decision tree what we do. So here we have this one, and here just we do it like this. Okay, using feature 1 and again feature 2, feature 1 like this. Just we try to grow in this way, correct? But here just we will not use this. What we will do, just we will grow for only one level. Okay, so these particular things, there is a funny name that is called the decision stumps. So let us suppose for here we do have feature 1 and feature 2. So what will happen? So using feature 1, just you have classified 2, only one level. Okay, so these are the basically decision stumps, these are not the trees. Okay, so using feature 1 and using feature 2, F2, you have another decision stump. From this decision stump, first of all, you have done a random sampling because weights are same, so you can do simple random sampling. And from here, just you are creating the decision trees, basically the decision stumps, not exactly the decision trees. So just we are using feature 1 and feature 2. So which stump we will take? Because we have, 2x variables. Out of this vector, you have 2x variables. So feature 1 and feature 2. We will use this and just will grow the decision stump. From here, let us suppose you have a cross entropy over here and you have a cross entropy over here. You have a cross entropy. So what you have, you will select where the entropy is minimum, that particular stamp will be selected as your first classifier. Let us suppose this is your first classifier. Okay, so using this feature 1, you have chosen this particular classifier. If using this feature 2, let us suppose if the cross entropy is less, then you have to choose this particular stamp. So for our particular purpose, let us suppose we are taking this F1. Okay, this is your first stamp, and just we are taking this as a T1 as a first step. Okay, so you have built one particular classifier. After when you have classified this, just you have made the classifier, and again in this classifier, just you are giving this input, you will get some sort of predictions. You will get some sort of predictions. Out of all these predictions, so many cases you will be able to correctly classify, and so many cases you will be able to you will simply misclassify all those couple of things. That particular thing will be considered as the error term. So just in the first step, this is your prediction, and the error is 0 0 like this, and here there is a mismatch between y and this prediction. This is your 1, and these are the negatives, and these are also the predicted as a negative. These are so the error will be 0 in this case. Okay, so after that, what we have to compute, that is nothing but this. What is the total error? That is basically how this ET is coming. So how many ones are there? This is 3 ones are there. So corresponding weights, what is the corresponding weight of this? That is 0.1, 0.1 and 0.1, correct? So the total error will be 0.1 plus 0.1 plus 0.1, that is 0.3. And what is the lambda? Lambda is equals to half into ln of 1 minus total error divided by total error. This particular thing, you have to build this lambda. So from here, just you can compute this lambda. So this ET 1 minus 0.3 divided by 0.3 log of this one into half. This is your lambda, correct? Now, how can we get the next weight for the next iteration? So because these are the misclassified, so in the next step, what we have to do, we have to give all these misclassified, basically which are the basically misclassified over here. These are basically the weak learners. So in the next steps, we will give the more weightage to these weak learners. That is our main intention. So we have to keep the weight of these of these weak learners in such a way the weights will be more than the strong learners. Okay, what are the strong learners? In the first step, which are classified properly, those are the strong learners. So what will happen? So what is the lambda t? Lambda t equals to half of this one. Just we will calculate this lambda t. Now what will be the weight? Weight is nothing but, from this formulation you can get this weight. Weight is equals to wi, this previous wi, this into e to the power lambda t. What is the e to the power lambda t? This one, this e to the power 0.42. So what you can compute, that is for the weak learners, and for the strong learners, just you have to make this this is plus lambda t, this is the minus lambda t. For the strong learners, what will happen? Let us suppose for the strong learners, you have the lambda, that is 0.42. For the weak learners, what will happen? Wi e to the power lambda t, correct? So what will happen? Wi is your previous w, this one, and e to the power lambda t. What is the e to the power lambda t? That is nothing but e to the power, this is not, don't confuse about this t is the tth step, not something multiplied or something service like that. That is basically the tth step. Okay, so e to the power 42. So from here you can compute this, that is your 0.153. For the strong learners, what will be this? How this will come? That is nothing but 0.1 into e to the power minus 0.42. From here you can easily compute it, correct? So if you, now the weight is generated, now we have to compute the normalized weight. What is this normalized weight? Earlier, if you can see, all the summation of all these 0.1s make 1, correct? Because we do have the 10 samples. Over here, what will happen? So this summation of all these may not compute 1, because just we have to compute in such a way, in weight, sum of all these weights will be 1. So we have to normalize it. How can we normalize it? Just this divided by sum of all these values, sum of all this particular formulation already written over there, win equals to wi divided by summation of wi. Okay, so from here just we have to normalize it. Now, so we have taken a normalized weight. Okay, now just what we have to in the next step, just we will follow the same iterations. Now I will tell you how this oversampling and undersampling we will do from these normalized weights. Okay, so let us suppose from here, if you take the range that is 0 to 0.71, correct, from here 0.071 to 0.071 plus this. Okay, from here this will be this range. This will be the limit for if to this 0.071 plus 0.071, 0.071 plus 0.071, and let us say 0.071 plus 0.071 plus what is the upper limit of this, 0.167. Okay, so when we will compute at the end of the scenario, some for this particular sample there will be some lower limit and there will be some upper limit. This upper limit will be 1, because if you go for summing all these things at the end of the scenario, you will get 1. Correct. Now, how we will perform this oversampling and undersampling task? So we will try to generate some sort of fraction between random fraction between 0 to 1. Let us suppose we are generating some sort of fraction. Let us suppose 0.1. Correct. In the first iteration. So which sample will be taken care for the next training? So let us suppose this particular thing, this 0.71, 071 to this one, because 0.1 our randomly generated fraction between 0 to 1, and this lies between this and this. So in the second iteration, this particular sample will be taken in the first training sample. In next step, we have generated, let us suppose 0.3, let us suppose. So in that case, what will happen? So in that case, which one will lie between this particular limit? So that particular sample will be chosen. So over here, how we are biasing, just we are oversampling or undersampling. Let us suppose over here, for those couple of learners, these are the weak learners, there will be the higher chance to be selected for the next iteration. Why? Because this band will be much more wider than the weak learners. For the weak learners, the band is the width of this band is only 0.065, and for strong learners, width of this band is 0.153. If we generate, let us suppose, let's say n number of random samples, so that will be much higher chance that these particular weak learners will be selected for the next iteration. I think this is pretty clear. This is a pretty clear concept to you. So now, how can we do it? How can we how can we finally classify this from this? So from this, we'll generate some sort of random samples using this particular thing, using oversampling and undersampling, and we will make the next T2, that is your again decision step, using the same rule. We will use it over there, and so on and so on. What we will get? You will get some sort of T1, T2, T3, T4, T5 like this. So up to how many steps you want to proceed from up to that step, you can get all these T's. Okay. So for each and every step, you do have one lambda. Lambda 1, lambda 2. You had seen this in the first step. This is 0.42 is your lambda. Similarly, in the second step, you will have a lambda. In third step, you will have a lambda, like this, all these lambdas. So just you have to create this one. So summation of GTs are nothing but the T's, nothing but T1, T2 like this. Okay, these are the these are the terms at each and every stage, not G into T, that G suffix T. Don't misinterpret it. Okay, so sum over lambda at Tth step into the decision stamp constructed in the Tth step. So let us suppose taken a pictorial view, you will get an understanding. Let us suppose just we are using one decision boundary, because we are using one feature only for each and every step, because we are creating the stumps, not the whole entire fully grown tree, for only one step tree, one level tree basically. So let us suppose for a particular purpose, so this is your lambda 1 for this particular example. just you have created this boundary in this if beyond in this direction, just you will have the positives and this in the negatives. Over here just we have misclassified this, red marked these positives because it should be positive over there. So in the next iteration, so what will happen, this particular red mark positives will be given the more weights. So you have created next decision boundary and next decision boundary like this. So in the here you can see that these are the misclassified negatives. So in the next iteration this will be given the more weights, and just over here just will create another decision boundary. So and these are the corresponding lambdas. So what you have to do, so 0.42 into this let us suppose you have a next entry f1 and f2, and for that you have to predict it. Suppose you have pushed this particular thing in this particular decision stem that is giving some output into lambda 1, you do have the lambda 1 earlier, plus 0.65 into something like into just that will predict it from the next term into this plus 0.9 into that will be predicted from the third distance term, and just you have to add it all these things, and you have to get the signum function, and you will get the output over there. You can combine all these things, you will get the decision boundary like this. Okay, these are the earlier decision boundaries, these are the blue marks, and just if you combine, if you go for the majority vote like this, we'll not directly go for the majority vote over here, just we'll multiply that with lambdas and operate the signum function, and we'll get the output from it. Correct. I think you have enjoyed the video, and like my video and subscribe my channel. Stay tuned for the next video. Press the bell icon. Okay. Today, bye bye.